Okay, we ended on 3.28. There we go. And make sure you have your best friend ready to go. So I'm going to talk about that. but if you have your handheld eye clicker, you should have it. So I'm going to talk about it. As a reminder, everybody, those masks need to cover mouths and noses. Mouths and noses, please. All right, so happy Tuesday, everybody. So what do you get when you cross a snowman and a vampire? Frostbite. Now, I'm going to tell y'all yesterday's joke just because I liked it so much and feel the need to share it. So what do you call a man lying at your doorstep? You call him Matt. Thought that was funny. All right. So make sure you go in and put your name on the seating chart. So here, whoa, not there, here. Make sure you put your name on the seating chart. Okay. Now, something that a couple of people had emailed and asked for is a few like supplemental videos on how to do certain problems. And people have asked for different topics within the chapter. And so what I thought I'd do is make it available to everyone. So if you look on the chapter 3 material, right? So all I did was go to unit 2. I went to chapter 3. And here are the lecture slides. There are the in-class problems that we do. And then it's the normal videos. And then at the very bottom, I put you an extra resource. So chapter 3 video resources. These are not required. But like if you're struggling with the crisscross method for writing formulas, there's an extra video, right? There are extra videos for lots of different things within this chapter. And so I thought if I'd make it available to one person, I'd make it available to everybody. Okay, so this is a good resource for y'all. Okay, so now that you know how to find that. All right, what's on my list? Oh, it looks like we're not going to quite finish chapter 3 today. Last class, we almost finished. We got to the last section, but we didn't quite finish. So what I did was I moved the homework from being due on Wednesday to being due on Friday. So we'll finish it up real quick at the beginning of Thursday, and then it'll be fine. Okay, so keep watching, keep the regular schedule up. We're just a little bit behind in class, and we'll catch back up. Don't worry. Okay. All right. So the other thing is iClicker. Okay, I want to do iClicker questions, but here's the deal. So I'm going to put this up here, and I'm going to start a poll. Now, there are people who did the book bundle whose subscriptions are now expiring, right? Okay, so we ran into this issue earlier in the class period. And what the iClicker website had said was that if you purchase an iClicker, a handheld iClicker, you would automatically get subscription to the iClicker site so that you could do the one on your phone, right? So through the book bundle, I said iClicker is required for class, right? So through the bundle, you got the handheld iClicker, right? But it just gave you the 14-day like trial version, right? So now today, when I'm asking you to do iClicker, it's asking you for a code if you're using it on your phone. Yes? Yes? It's telling you to buy it, right? Okay, don't buy it yet. So I'm gonna talk to the bookstore and see what the deal is, because I don't know, because this just happened last class period. But regardless, you can use your handheld iClicker, right? So you don't have to use your phone. You can use your handheld iClicker. So if you have your handheld iClicker with you today and it's telling you that you need a subscription, put your phone away and pull out your handheld iClicker. Now, I'm not going to make it due for points today because of this issue that's going on, and I want to talk to the bookstore, but it's driving me crazy that I can't do iClicker questions because I think they help you so much. But I want to talk to the bookstore. So we're going to do some iClicker questions, and you're welcome to like click in, but I'm not going to grade them so that it doesn't bring down your grade if you're having a subscription issue. Okay. And so I'll try to talk to the bookstore today, but if I can't get to talk to them today, I will talk to them first thing in the morning tomorrow. And once I have information, I will send out an email to everyone in the class so that you all know what the deal is. Sound good? Any issues that does not cover? Cool. Okay, I hate this book bundle. I'm recorded as saying that. I don't care. I hate the book bundle. Do y'all like the book bundle? Okay, I'm on Faculty Senate, so that's really good to know that my students, y'all are saying this, right? Okay, All right. Okay, I'm gonna tell them that. All right, so you can click in if you'd like to click in on this. If you want to know that your handheld eye clicker is working, you know, this might be a really good test of that before you actually have to use it, if you have to use it on Thursday and not your phone, right? So you can click in. I'm just not going to like grade it within iClicker. So how many valence electrons are in an atom of magnesium? Just call it out. We have two. Whoa. We have two valence electrons. What does that mean the charge is? +2. Why is it a +2? Because we're losing 2 electrons, right? It's easier to lose 2 than to gain 6. Okay. Elements in group 8A or 18 are called noble gases because they have how many valence electrons? Just call it out. How many? 8, D8, except for helium, right? These are one exception who's happy with 2 because that completes his outer shell. All right. How many protons and electrons are present in a sulfide ion S2-? So let's look at protons first. So look at sulfur, it's element number 16. So how many protons? We have 16. Okay, now electrons. Be careful with this. Protons are 16 and they're positive, and I have to have some number of negative in order to end up with a +2. So how many electrons are in this sulfide ion? 14. It's -2. I'm sorry, it's -2. Whoa, whoa, whoa. Why did I put a plus? -2. -2. Okay, now, what do we need? 18, -18. That charge matters, right? Charge matters. Okay, so what are we doing? +16, 16 protons and 18 electrons, right? Okay, oh, I missed my place. Here we go. Okay, what ions are formed when magnesium transfers electrons to chlorine? So go find magnesium. Magnesium's in what group? 2 + 2. Chlorine's in what group? 17, so it has a charge of -1, and we just don't put the 1, right? And in really, you put the plus after, but it doesn't really matter. I think your homework system, it cares. Does your homework system care? They want it after, right? Yeah. Doesn't really matter. Okay. Now here's one I'm going to give you a minute on. Select the correct match between the name and the formula unit. So take a minute, think about it. I'll even do it to see if we can click in on it. Let's do it. Or at least look at our response results. So if you can click in. Math needs to be covering noses. So I'll give you all till 2 minutes. Okay, so what are we saying? A or B? We're saying A or B. Okay, so turn and talk to your neighbor and find out what they think. Click in again.
Sorry, I had to think about it.
Okay, so I think we're kind of thinking B keeps getting more B's. Okay, so let's talk about each one. Potassium chloride, KCl2. What group is potassium in? 1, so it's a +1. Chlorine's in group 7, so it's a -1. So what should you get? Crossover, K1Cl1, but we don't write the ones. So that's not right. Okay, magnesium sulfide. Magnesium is in what group? 2, so it's a +2. Sulfur is in 6, so it's going to gain 2 more electrons, so it's a charge of -2. So Mg2S2 reduces to Mgs. Okay, so that one's right. Aluminum fluoride. Aluminum is always going to be a +3, right? Fluoride is going to be -1 because it's a halogen, so that's AlF3. So that's wrong, right? Okay. Tin 4 oxide. Sn is 10. So 10 is one of those transition metals, right? So what do we have to do to get the charge? Look at the Roman numerals. So we get, that's where we get the 4. Oxygen is always going to be group 16 or group 6, so a charge of -2. So we get Sn2O4. Can we leave it like this? What does it reduce to? 2 divided by 2 is 1. 4 divided by 2 is 2. So what do we get? SnO2. So do we have the same answer? No. Okay. Copper 1 bromide. Copper again is one of those transition metals. So we look at that Roman numeral and we know copper is a +1. Bromide, halogen. So it must be a -1. Crossover, Cu1, Br1, not a 2. Okay. Got to get good at that. All right. Let's close that. All right, now stop that. So we will be doing iClicker in some way, shape, or form on Thursday. So if you bring in your handheld iClicker, it works. Okay, it works. All right, but you should be able to use the thing, but it's fine. Okay, I will talk to the bookstore. I need to get over it between now and then. All right, so one thing I want to talk about before we do new stuff, right, is kind of how to do things in reverse of what we were doing on Thursday, right? On Thursday, we said, okay, take these two things and make a formula with them, right? Make an ionic compound and write the formula. So what if I give you a formula and ask you, what are the charges on the ions that make up that ionic compound? Can you do that? So what about NaCl? How do I do that? What are the charges? Pretty simple, right? I can go to the periodic table and I can go get Na. What is Na? +1. What is Cl? -1, right? So that's pretty easy. But what you can do for more complex things is what's called the reverse crossover, NaCl, right? There's a 1 and a 1 here. It's understood, but it's there. So all you have to do is reverse crossover and make sure you remember which one's the anion and which one is the cation. It's the same thing, right? But there are some cases where you have to be careful of doing that. And I'm going to give you an example. What about FeO? Can I do the reverse crossover with this? We're just assuming there are ones there, right? So can I just cross them over and say oxygen should be a -1, iron should be a positive one. Well, what do you know? Do we know what iron has to be? No, it's a transition metal, so we can't do that. But we know oxygen. What does oxygen have to be? Must be a -2, right? So if you do that and you multiply both of these by whatever number will get you the right charge, it'll work. So this is Fe2+ and oxygen 2-, and it works. See that? So it's the same thing we did before, except you got to go backwards. Okay, let's do another one. Let's do another one with iron, because iron's one of those transition metals and keeps you on your toes. Okay, so FeC2H3O2. What's the charge on iron and what's the charge on acetate? On 2, sorry. What do you think? We take it and do the crossover. Iron would be a 2+. There's really a 1 down here. So if we took this, that would be a 1-. Is that right? How do you know? Well, iron, you can't tell, right? But what about acetate? Your best friend, open your best friend up to your polyatomic ion table. What is acetate? I did give you acetate, yep. It's a -1. So this is correct, right? I was able to do the crossover. So the iron is a 2+, the acetate is a 1-. So if you have a polyatomic ion, you can use it to check. Okay, how about this one? We'll do one more. Okay. One more. Okay, we're going to do FeCO3 2. What is iron and what is CO3? What are the charges? Do the crossover. What do you get? Fe is a 2+, and really there's a 1 down here. So CO3 is a 1-. Is that right? No, why not? You went to your best friend, right? And you got CO3 is carbonate. What's the charge on carbonate? 2-. So what am I going to do? Multiply both of these by 2. 2 times 2 is 4. A +4. 2 times -1 is 2-. Right? Good? Okay. So just be careful of that with your transition metals and things like that. Okay. Moving on. Any questions on that? Good? Okay. Now, we talked about everybody wants to be like the cool kids, right? What do the cool kids have? They have a complete octet. They have a complete outer valence shell. So we said, in order to get there, some elements will give and take electrons. What else could happen? They could share. They could be so nice to each other and share, right? That's covalent. We call it covalent because they are sharing valence electrons. So that's what we're going to talk about today, how those bonds form and why they form. So what you have to remember when you're drawing these compounds is that all of them are trying to get to a complete octet. Everybody wants to get to that complete octet. So one thing that you can do, let's start with this one, is that you can look at the individual molecules. So let's look at A. A is H2O. That's telling me that for one molecule, I have how many hydrogen atoms? 2. How many oxygen atoms? 1. Okay. If I want to know about the whole molecule, I have to understand the atoms that make up the molecule. So how many valence electrons are in hydrogen? Only 1. So I can do this with a Lewis dot diagram. Doesn't want to pick up my pen today, diagram. where I put each valence electron as a dot, right? So I have 2 hydrogen atoms. And what else do I have? Oxygen. How many valence electrons does oxygen have? 6. So what do I do with those valence electrons? Put them 1 on each side, and then you can pair them up. Does it matter which ones you pair up? Does not make a difference. Anywhere you want. Okay. If I want to draw a molecule that will have these atoms inside of it, what I need to do is figure out who's going to be in the middle and then how they're going to be arranged. So how many more electrons does hydrogen need to be complete? Needs 1 more, right? VE. How many does oxygen need? However many more electrons the atom needs is how many bonds it can make. So how many bonds can hydrogen make? Only 1. That means I can only link 1 element to hydrogen. So can hydrogen be in the middle of my compound? No. What does it have to be? Oxygen. So anything like hydrogen or any of the noble gases cannot be central atoms. They have to be peripheral atoms. Okay. So I'm going to put oxygen in the middle, and I'm going to put hydrogen around my oxygen. And put in your dots, just like you did on the dot diagram, like that, right? What happens to create a covalent bond? Oxygen is going to share an electron with hydrogen. Hydrogen is going to share its electron with oxygen, right? So what we do is, instead of drawing 2 dots, what we'll do is we'll draw a line. And that line signifies a bond, and it signifies that these 2 atoms are sharing 2 electrons between each other. So these 2 electrons spend time with hydrogen, and they also spend time with oxygen, right? They're very nice. And we do the same thing over there. So we're saying that oxygen is bound to each hydrogen with 1 bond, and then on that oxygen are 2 pairs of valence electrons. Now, do you see water drawn like this anywhere in your book? Nope, why not? How do you see it drawn? See if I can extend the page. You see it bent, right? So oxygen in the middle, hydrogen is pointing down, and then 2 pair like that, right? That's how you see it. Why is that? So you see these electrons that are participating in the bond? Who do they hang out with? Hydrogen and this oxygen, right? These electrons in this bond hang out with oxygen and hydrogen. What about these electrons? Who do they hang out with? Only oxygen. They're only friends with oxygen. They only hang out with oxygen. And remember, all electrons are negatively charged, so they repel each other. So because these 2 electrons are spread out over a greater distance, they don't take up as much room as these pairs of electrons. So these 2 take up more space, and what you end up having is a molecule like this, right? It's bent, and it has 2 sets of valence electrons that are pushing those bonds down that give it a 3-dimensional shape. Now, we're going to talk about 3-dimensional shape in the last section of this chapter. It's cool. You don't have to know it until then, but I want you to know why you never see water drawn like this in your book. Okay, make sense? Okay. So you can do it like this. This is kind of the intuitive way to do it, but I also have a different way that I like to teach drawing Lewis structure. And I call it the needed available shared method. Anybody use that before coming here? No, nobody. But it's a formula. If you do this, you're going to get the right answer. It's not arbitrary. So the way that you do this is you do your needed valence electrons, and I abbreviate that N. And then you look in the molecule and you look at the available. Okay, that's not available. valence electrons, and then the shared valence electrons. And I put it NaS. Okay, so my needed, how many electrons does each atom in this molecule need to be happy, to look like the cool kids? So let's take each atom by itself, right? H2O. Hydrogen. How many valence electrons does hydrogen need to be happy? Total number to be happy, not how many more does it need, but total. 2. How many hydrogen atoms do I have? H2 tells me I have how many atoms? 2. Okay, so that's the needed from hydrogen. Now we have to look and we have to add that to oxygen. Oxygen needs how many to be happy? Total. Most elements will say this. 8, right? Most need a complete octet. Hydrogen's kind of funky and it doesn't. How many oxygen atoms do I have? Only 1, because there's no subscript, so it's understood as 1. Okay, now I need to know how many are available. Oh wait, let's total this up. What do you get total? 12, right? Okay, available. In hydrogen, how many electrons are available? So look at hydrogen. How many valence electrons does hydrogen have? How many does it have? Only 1, right? When you drew the electron dot diagram, how many electrons did it have? 1. How many atoms do I have of hydrogen? 2. Oxygen. How many does oxygen have? 6. How many oxygen atoms? Okay, for a total of how many? 8. Okay, so to get your shared, you subtract your needed minus your available. So 12 minus 8 is how many? 4. This molecule needs to share 4 valence electrons for everybody to be happy and to have that complete octet. But if I were going to draw a bond, how many electrons are participating in that bond? 2. So if I take my number of valence electrons that need to be shared and I divide by 2, I get the number of bonds. That gives me 2 bonds, right? So I know in my molecule, I'm going to have 2 bonds. But my question is, am I going to have any electrons left over that are going to be lone pairs? So what I do is I do my available minus shared. This is going to tell me my number of lone electrons, valence electrons, right? So how many did I have available to be used? Right here. How many did I have available? 8, right? Now, how many did I use inside of my bonds? I used 4. So how many valence electrons do I have left to put on my molecule after I add 2 bonds? 4 valence electrons. Okay, so I know I have H2O. I know I need 2 bonds in here, and then I'm going to have 4 valence electrons. So I know hydrogen is not going to be on the outside, so I put oxygen in the middle, and then I'm going to put my hydrogens on either side of my oxygen. I'm going to use a bond each. I'm going to use up these 2 bonds to connect my oxygen to my hydrogen. Does hydrogen have complete octets? Yes, not really. It doesn't have 8, but it's happy, right? Is oxygen happy? No, count the electrons around oxygen. 2 for each bond. So that gives me 4 electrons around oxygen. Is oxygen happy? No, but what do I have? I have 4 valence electrons, and I put them in pairs on the atoms that need them to complete their octets. So I know we knew how to draw water, but I just wanted to show you the different methods that you can use in order to draw these molecules. There's not one way, there are multiple ways, and we'll do a little bit of both today, okay? All right. Scroll down. Give me some more space. This page is going to be huge. Okay, so B. What is? Let's see. Where am I? What is B? C3H8. Right. All right. So let's do needed, available, shared. And you know how I remember this? The order. Drawing Lewis structures is kind of nasty. Yeah, nobody wants to do it, right? NAS. Okay. So needed. Carbon needs how many? Everybody wants how many? Everybody, no matter who. 8, unless you're hydrogen or lithium, but you know. Okay, 8. How many atoms? 3. Now I need to talk about hydrogen. Hydrogen needs how many to be happy? 2. And how many atoms do I have? 8. Okay, available. How many are available in carbon? 4. How many atoms of carbon do I have? 3. Okay, how many available in hydrogen? 1. How many atoms of hydrogen? 8. Okay, so now how many total needed do I have? That's 8 times 5, that's 40. And then how many available do I have? That is 20, right? Okay, so look at the difference. The difference between what you have available and what you need is what you're going to have to do to share. So needed minus available gives you how many? 20 valence electrons. How do I get to bonds? Divide by 2 and I get 10 bonds. Am I going to have any lone pairs left to put on the molecule? I do available minus shared. 20 minus 20, none. So I'm going to have no lone pairs to assign. Everything should be happy just by connecting with these 10 bonds. So how can I connect 3 carbons and 8 hydrogens to make everybody happy? Is hydrogen going to be in the middle? No. So let's put some carbons in a chain. Okay, so that's like the middle of my molecule. Now what am I going to do to those carbons? I've used up 2 bonds. How about we give each carbon at least 1 hydrogen and see what happens? Right? So the hydrogens that I put in are now happy. Are the carbons happy? No, and I've only assigned 3 out of the 8 hydrogens. What should I do? How about we give everybody another one? Am I good? No, what do I need to do? 1 more hydrogen on those end carbons. Now is everybody happy? Yes. So you could have done this by saying carbon is 4, right? Carbon is 4 and linking them together, and then hydrogens are 1 and linking those together. You could have done it either way. Okay, I'm not telling you right or wrong. I'm just telling you there are multiple ways to solve those problems. But the more complex they get, the nicer the needed, available, shared gets. Okay, N2. And the cool thing with this is it's gonna be very nice in this one. So let's do this one the dot way first. So nitrogen, if I'm going to draw the Lewis dot diagram of nitrogen, how many valence electrons? 5. 1, 2, 3, 4, 5. So I'm going to draw another nitrogen. 1, 2, 3, 4, 5. Okay. What do I do? Create a bond, right? And I'm good. Am I done? No, why not? I still don't have complete octets around my nitrogen. So the bond counts as 2, 2, 3, 4, 5, 6. I only have 6 electrons. So what am I going to do? Create another bond. Does that give me 2, 4, 5, 6, 7? Am I happy now? What do I need? another bond. So really, when you draw it, you would draw it as N with a triple bond, and then each nitrogen has a lone pair on it. Okay, could you do the needed available shared with this? Sure. So nitrogen, how many valence electrons does it need to be happy? 8, and we have 2 atoms, so that is 16. Available is only 5, right? We have 2 atoms, so that's 10. So 16 minus 10 is 6. So 6 valence electrons divided by 2 tells you 3 bonds. I like this because I look at this and I say, okay, I know I only have 2 atoms, so therefore I must have a triple bond, right? It's kind of a nice method. So available minus shared, I had 10 available. I used 6 in bonds, so I now have 4 valence electrons left. And I just spread them out to make complete octets for everybody. But it's up to you, whatever you want to do. Okay, we got one more on this one. SiF4. SiF4. Okay, let's do needed available shared. Okay. And one trick I do want to mention is that when you're writing these molecules, a lot of times, this first atom right here is going to be your central atom. A lot of times, not always. What about H2O? Was your first atom the central atom? No. So it doesn't work all the time, but a lot of times it works. Okay. All right. So needed. Silicon, how many? 8. How many atoms? 1. Fluorine, how many does it need? 8. How many atoms? 4. Okay. Now, available. Silicon. How many? I thought I was hearing 6. I was like, 4. Okay. Fluorine, how many? 7. And I have 4 atoms. So how many needed? 8 times 5 is again 40. Available? 32. Subtract, what's our difference? 8. To get my number of bonds, I divide by 2, I get 4 bonds. And it kind of makes sense. Fluorine is a halogen, right? Fluorine can only make how many bonds? Only 1, right? So you're going to have silicon in the middle, and then you're going to have fluorine surrounding it, right? But now my question is, do I have lone pairs left? A lot of times this is where this is nice too. So I have 32 available. I used 8 inside of my bonds. What's the difference? I have 24 valence electrons left. Where am I going to put these 24 electrons? Can I put them on my central atom? Why not? It's happy. 2, 4, 6, 8. Silicon's happy. Don't mess with it. Is this fluorine happy? It's only got 2. How many more does it need? It needs 6 more, right? So 6, 12, 18, 24. Awesome. Pretty neat. Y'all got this. Y'all got this. Totally. All right, so let's do a few more. All right, draw the correct structure for each of the following covalent compounds. Chloroform. All right, A. So CHCl3. You want to do needed available shared, or you want to do it? I kind of like needed available shared. No, some people don't. It's cool. If you didn't learn that way and you've learned it already, do your thing. It's cool. Doesn't matter. Okay, needed, available, and shared. How many does carbon need? 8. Hydrogen, and there's only 1. Hydrogen needs 2. Chlorine needs 8, and we have 3 of them. So what do we got? What do we got? Okay, and then available in carbon. 4, available in hydrogen. 1, available in chlorine. 7, and we have 3. So what do we get? Our difference between the two is 8. So we have 8 valence electrons that we're going to share. Divide by 2, that tells us our bonds. We're going to have 4 bonds. What's going to be my central atom? Something that's going to be able to make more than 1 bond, right? Can hydrogen make more than 1 bond? No. Can chlorine make more than 1 bond? No. So my central atom has to be carbon. And since all of the other ones can only make 1 bond, we have to put them around the carbon that way. So I'm going to give each one a bond. I've used up my 4 bonds. Do I have any remaining? Available minus shared, 26 minus 8, how many? $18. So am I going to put them around carbon? No, carbon's happy. Hydrogen? No, hydrogen's happy. So we're going to put them around chlorine to complete chlorine's octet. That is 6, 12, 18. Okay. All right, AsCl3. All right, so let's do this one. We're just going to draw it in our Lewis dot. Okay. As, how many valence electrons? Excuse me. We have 5. So I'm going to go 1, 2, 3, 4, 5. Now, I have 3 chlorines. So I'm going to put my chlorines around my central atom so that excuse me, so that I can make a single bond, right? Chlorine can only make 1 bond because it has how many valence electrons? 7, right? So if I put a chlorine and I go 1, 2, 3, 4, 5, 6, 7. So then I can connect these 2 and make that a bond, right? I do the same thing. 1, 2, 3, 4, 5, 6, 7, and I make that a bond. And then I do again, chlorine, and really that should be kind of down. Chlorine, and I get 1, 2, 3, 4, 5, 6, 7, and then I convert those dots to bonds. Right? Either way is fine. So when you look at a molecule like that, you're looking at something like this, right? Where you have a lone pair on top and that lone pair is taking up a ton of space. And so instead of it being flat, right, it's actually kind of pyramidal. If you lay it, it kind of sticks up, right? Okay. C, what is C? Cl2. Now Cl2 is really easy. Cl2, I know that Cl has how many valence electrons? It has 7. So how many bonds can it make? Only 1, right? So if I have 2 chlorine atoms, they can only make 1 bond with each other. So if I put my 7, 1, 2, 3, 4, 5, 6, 7, and you notice I put my 1 by itself to where it can participate in a bond. I kind of plan ahead. 4, 5, 6, 7, and then all you have to do is connect the dots. All right, just be careful to connect the right dots. Okay, so you don't have to use it for everything, but you can. You could do needed available shade for all of these and it would work every single time. I will never give you one where it does not work. There are exceptions, but I won't do that to you. Okay, C2H4. I like to do the carbon. Carbon's pretty easy, right? Because carbon likes to make 4 bonds in general. So if I take 2 carbons and I have 2 hydrogens, right? If I go 1, 2, 3, 4, 1, 2, 3, 4, and I put my hydrogens and my hydrogens, I can bond to the carbon, connect my carbons. Is anybody happy? Hydrogen's happy, but is carbon happy? No, so what am I going to do? Make some more bonds. So then I end up with H, C, triple bond, C, H. And how do I know that's correct? Because if you pick any atom, they should either have 2 to be happy or 8 to be happy, but they should be happy. So carbon has 2, 4, 6, 8. This carbon, 2, 4, 6, 8. And then the hydrogens have 2. Okay. All right, so we've talked about the 2 different kinds of compounds forming, right? Covalent compounds and ionic compounds. How can you know the difference just by looking at either the name or the formula of the compound? All you have to know is what type of element is inside of that formula. So what are the rules, right? I did this on the video. To be a covalent compound, what must you have? A nonmetal and a nonmetal, right? But every other way will form an ionic compound. So if you have a metal and a nonmetal, you're ionic. If you have a polyatomic and a nonmetal, you're ionic. If you have a metal and a polyatomic, you're ionic. Or if you have a polyatomic and a polyatomic, you're ionic, right? So it's kind of like, is it covalent or not, right? It's kind of the easier way to think about that. K2O. What do we have? What's K? Metal or non-metal? Metal. O is a non-metal. So if I have a metal and a non-metal, what am I? I'm ionic. Carbon and oxygen. Carbon is a non-metal. Oxygen is a non-metal, so it must be covalent. GAF. Gallium is a metal. F is a, fluorine is a non-metal, so it must be ionic. C2H6. Carbon is a non-metal. Hydrogen is a non-metal. It must be covalent. NiCl2. Nickel, metal or non-metal? Metal. Chlorine, non-metal. So a metal and a non-metal make an ionic. Oh, now we have more than 2 elements. So am I looking for, I know if I have more than 2 elements there, I'm looking for a polyatomic ion. Is my polyatomic ion BAS or is it SO4? SO4, how'd you know that? Some people know them, but what could you do if you didn't know? You go look on your best friend, go get your best friend, and your best friend has all the ones that you need to know, okay? All right, so barium is what? A metal. So a metal and a polyatomic make a ionic compound. SO2, sulfur and oxygen. Sulfur is a non-metal, oxygen is a non-metal, and non-metal and non-metal, covalent. N2O, nitrogen is non-metal, oxygen is non-metal, must be covalent. NH4Cl. So what's my polyatomic? NH4 or H4Cl? NH4. So if I have a polyatomic and chlorine is a non-metal, that must be ionic. Okay, SiH4. Careful with this one. What is SI? Who's your best friend? What's your best friend say? It's a metalloid. Oh, it's a metalloid. So in this case, because it's not a non-metal, a metal and a non-metal, because it's a metalloid, it's going to be covalent. So this is a metalloid. All right. So now we know how to draw them. We know how to identify them. Now we're going to figure out how to name them. So when you name covalent compounds, you do the same thing with the ending. You remember how ionic compounds, what did your anion end in? IDE. So what you'll notice is they all end in IDE. So they're all going to do that. But now what you have to do, because you're not worried about charges, right? You can't use charges to determine number of atoms in things. You actually have to say how many atoms of each are there. And so we do that with prefixes. Am I making you memorize your prefixes? No, where are they? They're in your best friend. Take out your best friend. It's on the same page as the electronegativity values. Okay, so if I have one nitrogen, what should I call that? You would think it would be one is mono, right? So why is NO2, why is it nitrogen? Why isn't it mononitrogen? If it's the first element and there's only one of it, you don't say it. Okay. So nitrogen dioxide. Here, there's only one, and the first one is phosphorus, so we don't name it. We just say phosphorus, and there are three, and that's trichloride. So let's do this one. N2O4. Oh, and before I forget, I had a boo-boo on the video. Right? Anybody else catch it? It was H2O, and I called it dinitrogen monoxide. What should it be? Dihydrogen monoxide. Now, they did this thing. It's really funny. You can Google it. Just to prove how little people understand chemistry, they on university campuses, they've done this. They've started like this petition to ban dihydrogen monoxide, and it's terrible for you in huge quantities, and they list all this facts about dihydrogen monoxide, and people are signing away that it's terrible. It's water. It's water. Right? But if you don't understand the naming system, it sounds foreign, but is it? It's not, right? So just because something sounds like a chemical, well, everything's a chemical, right? Ask a chemist, everything's a chemical. So just because it sounds foreign doesn't make it bad. And that's one thing that y'all now understand. And, instead of saying, hey, can I get a glass of water? Next time you go out, say, can I get a glass of dihydrogen monoxide? See what they do. See what they do. Okay. N2O4. How do I name this one? Dinitrogen. It really is nitrogen this time. Dinitrogen. Tetra. T-T-R. Now, if it's two vowels next to each other, you typically drop the vowel on the prefix. So you drop the A and you just say tetroxide. But I'm not grading on that. Okay. I'm not grading on that. But just realize that that vowel will go away. Okay. Carbon monoxide. How many carbons do we have? One, but we don't write it. How many oxygens do we have? One. Carbon monoxide. Okay. P2O5. So what are we going to say? The 2 means di. P is phosphorus, and then 5 is, look on your table, penta, but we don't put the vowel because it's oxygen, because it'd be 2 vowels, so it's just pentoxide. Carbon dioxide, what's my formula? CO2. Okay, NH3, how do I name the nitrogen? Just nitrogen. And then I want to do my hydrogen. So 3 is trihyd. and I'm going to end it in I. I see a lot of people say nitrogen trihydrogen. Is that right? Now you got to make sure that that end is ending in IDE. Anybody know the common term for nitrogen trihydride? Ammonia. Ammonia. All right, so the next thing that we're going to do, a little more math, right? So however small that you think an atom is, it's smaller. It's like really, really small. So when you want to count something, the smaller it is, the bigger that counting unit is going to be. So for example, what is bigger, an egg or a sheet of paper? What's bigger? It has more mass. An egg has more mass, right? So what's our counting unit for an egg? How do we get them at the store? By the dozen, right? So that's 12 eggs in a dozen. But everybody knows that. Everybody knows what a dozen is, right? Okay, how about paper? How do you get paper at the store? Like in a pack, or technically the term is a ream. Anybody know how many sheets of paper in a ream of paper? 500. Do you want to go to the store and get 500 eggs? No, nobody's going to eat 500. Well, you know, if you're a restaurant, you know, that kind of thing. But we're not, right? So now, what's smaller, a sheet of paper or an atom? An atom. Like that was a ridiculous comparison, but really, really small. So I'm going to have something really big to encompass as many atoms as I want, right? So my relationship, right? 12 eggs in a dozen, 500 sheets of paper in a ream of paper, is in 1 mole, I have 6.02 times 10 to the 23rd atoms. Is that a lot? Times 10 to the 23rd. Like that. That's a lot. That's a lot. So no matter what element you're talking about, if I say I have 1 mole of lead, I have 1 mole of oxygen, I have 1 mole of chlorine, how many atoms am I going to have? 6.02 times 10 to the 23rd. If I said I had 1 mole of peanut M&Ms, how many peanut M&Ms do I have? 6.02 times 10 to the 23rd peanut M&Ms. That would like cover the surface of the earth. That would be a lot of M&Ms, right? Okay, but why could we use that term for atoms and not M&Ms? Relatively, M&Ms are huge compared to an atom, right? So when we look at the periodic table, you see the little red numbers on your periodic table, or I don't know what they are. Mine's printed not in color. What color are your numbers under the elements? They're black. Okay. So the little number underneath is telling you however many grams of that element are present in 1 mole of the substance. So look on the periodic table and pick oxygen. How many grams of oxygen are in a mole of oxygen? 16. How many grams of xenon are in a mole of xenon? 131.29, right? So what we notice, kind of like go down the periodic table, look at helium. In helium, I have 4 grams in 1 mole. Now, as we go down, what happens to that number? Go down to neon, go down to argon, go down to krypton. What happens to that number? It keeps going higher and higher. But think about it, right? As you go down, you get more protons, you get more neutrons. So it's a more massive element. So then a mole of that element is heavier, right, than a mole of a light element like helium. So it's important to understand that relationship between atoms, moles, and then the molar mass, the molecular mass of that element. Okay, so let's tackle some problems. Compare the number of atoms and the number of grams present in 1 mole of helium and 1 mole of argon. So it doesn't matter what it is for number of atoms. If I have 1 mole of helium, what does that tell me? You could do dimensional analysis because you're going to have to do dimensional analysis later. So I just say embrace it now. I want to get rid of moles. What am I trying to get to? Atoms. Do I have a conversion factor, excuse me, that will make that happen? Yes, it is 6.02. I did not give myself enough room, times 10 to the 23rd. So how many atoms of helium are in 1 mole of helium? Third atoms of helium. Now, what about argon? If I have 1 mole of argon, y'all just told me this. If I want to get rid of moles, put that on the bottom. I know in 1 mole of argon, I have how much? E times 10 to the 23rd atoms of argon. This is like saying, how many eggs are in a dozen eggs? 12. How many M&Ms are in a dozen M&Ms? 12. How many bagels are in a dozen bagels? 12, right? Doesn't matter. That's what a mole is telling me. Okay, so now let's do part B, number of grams present. So let me just erase this. Okay. Now, I'm still starting with 1 mole. I have 1 mole of helium. I want to know the number of grams present. How do I get that? I look on the periodic table and I find helium, and I look at that bottom number. What's the bottom number? So what that tells me is in 1 mole of helium, there are 4.003 grams of helium. So what do I have? Because I have 1 mole, 4.003 grams of helium. How about for argon? If I have 1 mole of argon, I find argon, and I look at that bottom number, and I know in 1 mole of argon, I have 39.95 grams of argon. So I have 39.95 grams of argon. Does it make sense? Yeah, because helium is a relatively light element. It's a light atom. It only has 2 protons and 2 neutrons, right? Why is this not 4? If it has 2 protons and 2 neutrons. What is that number at the bottom really? Average atomic mass of all of the isotopes of the element. So not all of the isotopes have only 2 neutrons. Some have more, which is why it's a little bit greater than 4. Okay. Argon has how many? It's element 18, so it has 18 protons and 18 neutrons. Well, that doesn't give me 40. What does that tell you about some of the isotopes? They have more neutrons, right? But it's a heavier element. It's a much heavier element than helium. So 1 mole is going to be much heavier for argon than it will be for helium. Okay. All right. So now let's do a few calculations with these relationships that we now know. So the number A, the number of sulfur atoms in 0.660 moles of sulfur. So I'm starting with 0.660 moles of sulfur. I want to get to atoms. I put moles on the bottom. Do I have a relationship between moles and atoms? Yeah, I do. I know there are 6.02 times 10 to the 23rd atoms. Which one am I going to? Sulfur. In 1 mole of sulfur. So my moles cancel. I'm left with atoms. Now you have to put it in your calculator. So get out those beautiful calculators. I'm ready to hear my second favorite sound, opening calculators. So I'm very strange, if you haven't noticed. But when you're at home the next time, like, you know, you're around your family, like, oh, would you grab me a glass of dihydrogen monoxide? Just to get their reaction. And then let me know how entertaining it was, because I know it's going to be entertaining. Okay, what did you get? Let's see, let me compare to what I got. Let's see. I wrote them all down here. Okay, I got 3.97 times 10 to the 23rd. Is that what I got? Atom sulfur. Okay. B, the number of moles in 15 grams of iron. So in this case, we're starting with 15 grams of iron and we want to go to moles. So can we convert straight from grams to moles? I know in 1 mole of iron, I look at my periodic table, I know I have how many grams? 0.85 grams of iron. So my grams cancel, what am I left with? Moles. In this case, I got 0.269, try the math, moles of iron. Is that what y'all got? Always check my math. Always check my math. Okay. C is the number of atoms in 66.0 grams of copper. So I'm trying to get to atoms, right? My goal is atoms. So can I go straight from grams to atoms? I don't really have that conversion. What do I have? I have grams to what? Moles. I know in 1 mole of copper, look up here at copper, I have how many grams? 0.55 grams of copper. So my grams cancel, I'm left with moles, but I want to get to atoms. So I need to do another conversion. So now I'm going to say in 1 mole of copper, I have atoms of copper. So what do you get? What do you get? I didn't write this one down. 1.66. Is that what y'all got? No? What y'all get? 6.25 times 10 to the 23rd. That looks about right because it's about 60 and about 60. Top and bottom, that would cancel. So you should be about 6 point something times 10 to the 23rd. Okay. All right. Now, that was just for atoms, right? But we're not dealing with just atoms. We always have molecules like dihydrogen monoxide, right? Like a water molecule. So when you're looking at the mass of individual molecules, you need to take into account each of the individual atoms inside of that molecule. So for example, ethylene, a ripening hormone, C2H4. There's an interesting, I'm going to take a little side trip real quick. So, you know, like when you have fruit and you leave it out on the counter to ripen, let's say you have bananas. You know, ever notice if you have an old banana and you put your new bananas next to your old banana, your new bananas ripen faster? Notice that? It does happen because the old banana is producing ethylene. And so it will help the other ones to ripen. So like if you want 10 ripe bananas for tomorrow, put an old banana in a paper bag and put your new bananas in and they'll ripen. You could do the same thing with rice. So if you have like a mango that you want to ripen faster, even if you don't have like another one, what you can do is you can submerge it in plain rice, like not cooked, like raw rice, put it in, and it'll actually trap the gases. And so that ethylene that's produced by that mango will stay by that mango and it'll speed up the ripening process. Things you never knew you wanted to know, right? Okay, so now we have to find the molecular mass of our ethylene. So if we have C2H4, we have to take into account the mass of each individual atom in order to find the overall molar mass of the molecule. So if you look at carbon, tell me carbon, what's the mass of carbon? 12.01. But do I only have one carbon atom? I have two. So I'm going to multiply that by 2. Is that the only thing in my molecule? No, I have hydrogen. So if I look, oh, I don't have hydrogen here, but it's 1.008 or 1.01. It depends on what periodic table you're looking at. Doesn't really matter. You'll get close enough. It'll be multiple choice and you'll get close enough. And there are 4 atoms. So this all together will tell you the molar mass, or 1 mole of this compound will equal this many grams. So what do you get? Let's see what I got. I got 100. Oh, no, that's the wrong thing. The wrong thing. I got 28.05. Is that what y'all got? And the units on that are grams per mole, because in 1 mole, I'll have 28.05 grams of ethylene. Okay, let's do B, citric acid, C6H8O7. So carbon is 12.01, just like y'all told me a second ago, but how many atoms do I have? I have 6. Hydrogen is again 1.008, but this time I have 8 of them. And now I have oxygen, which is 16, and I have 7 of them. So what do you get? I got 192.12 grams per mole. What y'all got? Okay. All right, the last one, C, sodium bicarbonate or baking soda, NaHCO3. So Na, sodium is 22.99, and we're going to multiply that by 1. Then hydrogen is what? 1.008, and we have 1 of them, plus carbon, 12.01, and I have how many of them? 1. Then I have oxygen, which we said was 16, and I have how many of them? 3. So what do you get? I got 84.01 grams per mole. Yeah. Right, we're doing good, right? So the bigger the molecule, the more atoms in the molecule, what could you tell me about the molar mass of that molecule? Which one has more atoms, A, B, or C? B has the greatest number of atoms. It also has the largest molar mass. Does that make sense? It absolutely does. It absolutely does. Okay, I think this is the last one in the section. All right, determine the number of molecules in a 200 milligram dose of ibuprofen, molecular formula C13H18O2. Okay, start with what you're given. You're only given one thing, right? What are you given? That you have 200 milligrams of your ibuprofen, ibuprofen, right? And you know, let's put the formula. Instead of writing ibuprofen, let's write C13H18, because we're going to need this, O2. Okay. Of everything we have talked about so far today, have we been talking in milligrams? No. So what do you think we need to do? Convert. So we need to get out of milligrams and we need to go to grams. What's my conversion? Do I have 1,000 grams or do I have 1,000 milligrams? I have 1,000 milligrams in 1 gram. Mass need to be over mouths and noses, please. Okay, now I have grams. I'm trying to get to number of molecules. Do you know what this is really similar to? Just like we said, number of atoms, number of bagels, number of M&Ms, number of whatever, right? So this is really similar to atoms, right? But we're not really counting atoms. We're really counting an individual molecule, right? How many of these molecules do I have? It's the same thing as if I pull off one atom and I say, how many atoms do I have? I'm going to use the same conversion. That make sense? Okay, so I'm in grams. I want to get to number of molecules. What am I going to do first? Can I go from grams to molecules or grams to atoms? I don't have that conversion, but what do I have? Grams to moles, grams to moles. So in 1 mole, I know I have some number of grams. How do I figure that out? I need the molar mass of C13H18O2. So carbon is what? 12.01 times, I have 13 of them. Wow. Hydrogen is 1.008 and I have 18. And then I have oxygen, which is 16. I only have 2 of those. So what do you get? $274. Now look, don't round at this point. We only round at the end. Don't round halfway through a problem because that'll end up messing up your math. So now I just take this and plug it in right there. 206.274 grams. But this is specific for my molecule, C13H18O2. Okay, I'm in moles. I need to go from moles to molecules in this one. So in 1 mole of anything, but this is C13H18O2, I have 6.02 times 10 to the 23rd molecules. So what do you get? Can't fit any more in my line. I'm running out of space. What do you get? I got 5.84 times 10 to the 20 molecules. Okay, and that is my final answer. So it looks like we did good. And we just have a little bit left for next time. Any questions? I will talk to the bookstore and I will get back to y'all. Fingers crossed, I can get it figured out. But if not, what do you bring on Thursday? Your handheld eye clicker. I know the phone's nicer, but bring the handheld eye clicker. Okay, any questions on Zoom? Don't forget to do the seating chart if you haven't. Okay, I'm going to go ahead and close the Zoom if nobody on Zoom has questions. Okay, I guess not.